Welcome. I wanted to go over the version of example 2 that we did in class. So for example 2, I changed the function. So instead of the function that you have in your note packet, we graphed the function f of x equals, there's already an f of x there. Let's take that one out. F of x equals the log of x minus 2 base 3 plus 1. So I want to remind you that in section 4.1, we looked at graphs of logarithms that had bases that were bigger than 1. Okay, so I'm going to remind you what the graph of y equals log of x base 3 looks like. So we switch it over to x equals 3 to the y power. And instead of putting in the x values, we actually put in the y values. So it's 1/9, 1/3. When y is 0, x is 1. When y is 1, x is 3. When y is 2, x is 9, and so forth. So we have that graph that looks like this. It goes through the x-axis at 1. It goes through the 0.31, the 0.92, and so forth. It's going to get close to the y-axis as a vertical asymptote, but going down. And so we have this shape. So if you look back at your 4.1 notes, we had this kind of shape for our logarithm functions when the base is bigger than 1. So if the base is greater than 1 on our logarithm, we're going to have this same basic shape, y equals the log of x base b. Okay, now what we have done over here with this function is we have, let's use the transformations. The minus 2 shifts it 2 to the right, and the plus 1 takes it 1 up, or up 1. Okay, now also notice that the domain of this thing, the domain of this function, is going to be everything, all x values greater than 2, because that argument, x minus 2, has to be greater than 0. So we have all real numbers greater than 2 as our domain, which means that we probably have, or we will have, a vertical asymptote at x equals 2, and that's the whole shift it to the right by 2. So our vertical asymptote, let's just write it down. Vertical asymptote is going to be the line x equals 2. So I'll put that on my graph. So here's x equal 2. Right? And then we should have, if we take a look at the points over here, we should be able to take all those points, move them 2 to the right and up 1. So how does that work? Well, let's build a little table of values. We'll take all of these values. We'll add 2 to the x, add 1 to the y. And I'm going to start with the 2 and 1/3. So we have 2 and 1/3 for the x, which is 7/3. We can write it that way as well. That's going to get me a y value of 0. That's going to be my x-intercept for this graph. So we don't have to go through a complicated process to find the x-intercept. We can just get it by moving around the original or simpler log function that we're transforming. Okay, so let's do the next one. If we add 2 to the x's, we add 2 to the x and 1 to the y, we get 3, 1. Let's check and make sure that works. If I do 3 minus 2, let me check it in the original function right here. 3 minus 2 is 1. The log of 1 to any base is 1. Add 1, I get, wait, 3 minus 2 is 1. The log of 1 to any base is 0. That's it. The log of 1 to any base is 0. And then 0 plus 1 is 1. Okay, let's move the next one. 3 comma 1 Should go to 5, 2. Let's follow that one through the function and make sure it really works. So 5 take away 2 is 3. Log of 3 base 3 is 1. 1 plus 1 is 2. It worked. The next nice point would actually be 11, 3. And that one's going to be off of our graph. So I think we have enough. We got 2 1/3 for our x-intercept. It almost looks like 2.5, but it's so hard in that little space. Then we have 3, 1. Maybe I'll change that out. Change it just a little bit. Make it move a little bit closer. We have 3, 1. We have 5, 2. So 1, 2, 3, 4, 5 is right here. It's going to be very flat coming out. All right. Oh, I made it probably a little steeper than it should be because I don't get to y equals 3 until I'm all the way out to 11. It's going to be right out here. Okay. And that's going to go down towards the vertical asymptote. Just using that idea of transformations, we get a really good picture of the graph. Okay. Let me clean up some of my mess here. All right. Next thing I want to do is go through example 7 because I did it a little differently in class. So I'm going to go through example 7. The video is great. Ms. Heckman does the example 7 in the video, but I did it a little differently. So I'm going to do it a little more like we did. Well, let's just get into it. Example 7. P of T is the population of the state of Utah in millions, T years after 1970. In 1970, Utah had a population of about 1.06 million. Assuming a constant growth rate of 2%, population of Utah satisfies. I'm going to take a look at this function. Oh, it's not a function. It's written as log of P of T equals log of 1.06 plus 0.02t. Okay, P of T is the population, time T is the number of years after 1970. Find the population of Utah as a function of T. So I'm supposed to solve this for P of T. I'm looking for the population as a function of time. So I need to solve for P of T. Population in 2018 is about 3.16. We're going to use the function P of T once we find it to see what our model would tell us. So what we're going to do, we are going to move this term to the other side. So we're going to subtract a natural log of 1.06 from both sides. That's an equal sign. Equals 0.02t. I am going to put these two logarithms together so that I have the natural log of, remember subtraction turns into a fraction, 0.02t. And then we're going to rewrite this in exponential form, or we could do what Ms. Heckman did in the video. We could take and raise or use both of those as, take both sides as powers of e. So as long as we're doing the same thing to both sides, but we'll just rewrite it in exponent form. In exponent form, it says the argument, P of T over 1.06 equals e, which is the base, to the exponent, which is the 0.02t power. Okay? And then I'm going to multiply both sides by 1.06, and I have successfully solved for P of T. Now, like I said, Ms. Heckman does it in the other video, and it works out great, and it's a wonderful method. But I just thought I'd go through and show the way we did it in class. So that's part of what we were supposed to do. We have found the population as a function of time t. We solved for P of T. Now, the other thing that I have to do is I am going to calculate P of, let's see, 2018. How many years past 1970 is that? That is 48. So I need to find the value of my function at 48, and then I'm going to compare it to what the actual population was in 2018. So 1.06 and then e to the 0.02 times 48. Now at this point, I'm going to grab my calculator. I'm going to round this to 2 decimal places. So I'm going to grab my calculator. Let me pull it up. And I'm going to put in 1.06 times, I'm going to do e, that second function with the ln, and I'm going to put in 0.02 times 48. I'm going to push enter. There it is, 2.77. So we're at 2.77 million. And now when we compare that to what actually happened, this is too low, which kind of makes sense because population in Utah has been growing fairly rapidly since, I don't know, for quite some time. So 2.77 million, our model is under the 3.16 million that was the actual. So it's below the actual 2018 population. And that is the end of this video.